Imagine stepping onto a world that looks exactly like Earth only to be crushed the moment you land. Kepler-452b tantalizes us with its potential for liquid water and life, but the reality on the surface is a nightmare of physics. With a radius 60% larger than ours, this planet possesses gravity, so punishing it would shatter human bones and trap any civilization that dared to rise. NASA found a candidate for biology, but physics suggests they found a prison. Is this truly a sanctuary for life, or have we just been captivated by a heavy, dangerous illusion? On July 23, 2015, humanity looked up at the constellation Cygnus and believed we had found a reflection of ourselves. NASA's Kepler Space Telescope revealed Kepler-452b, a world instantly branded by headlines as Earth 2.0. It sits in the habitable zone, orbits a sun-like star every 385 days, and promises the dream of a second sanctuary. But in the cold vacuum of space, labels are dangerous illusions. Kepler-452b is not our twin. It is a cosmic mirage separated from us by an abyss of 1,400 light-years. Consider the terrifying scale of that distance. The light we analyze today did not leave Kepler-452b this morning. It began its journey when Rome was collapsing and the Dark Ages were descending upon Europe. We are not communicating with this world. We are conducting an archaeological dig through photons. We are staring at a ghost image of a planet as it existed over a millennium ago. We cannot know if it is still lush or if it has already choked on its own atmosphere. The Earth 2.0 we celebrate may be a world that died long before we even invented the telescope. But the true horror of Kepler-452b is not where it is, but when it is relative to the life cycle of stars. Its parent star, Kepler-452, is a G2-type yellow dwarf, a near-perfect match for our Sun. But with one critical, fatal difference: it is 6 billion years old. It is 1.5 billion years older than our solar system. In stellar evolution, age is energy. As yellow dwarfs age, they do not fade quietly. They burn brighter and hotter. This star is pumping out 10% more energy than our Sun currently does. That 10% is the difference between a paradise and a pressure cooker. By studying this system, we are not looking at an alien world. We are looking into a crystal ball at Earth's inevitable future. This is exactly what our Sun will do to us in a billion years. Kepler-452b is a laboratory of planetary aging, a place where the delicate thermostat of habitability has likely been smashed by the relentless brightening of a dying star. We travel there not to find a new home, but to witness the forensic evidence of how an Earth-like world suffocates. To truly understand the hostility of Kepler-452b, we must descend from the safety of orbit and simulate the terrifying reality of standing upon its surface. In the popular imagination, a super-Earth implies a world that is simply larger, grander, and perhaps more majestic than our own. But physics dictates a darker translation on a rocky world, with a radius 1.6 times that of Earth and significantly higher mass. The surface gravity is estimated to be around 2.2 g. Imagine stepping out of a lander onto this alien soil. The moment your engines cut off, the sensation of weightlessness is replaced not by relief, but by a brutal, crushing assault. You immediately weigh more than double what you did on Earth. If you are an average adult weighing 180 pounds, you now carry the burden of nearly 400 pounds. It is the physiological equivalent of carrying another adult human on your back every second of every day without the possibility of putting them down. This is not merely an inconvenience. It is a constant, low-grade, lethal threat. Your body is a machine calibrated for one die. Here that machine is pushed to its breaking point. Your heart, suddenly tasked with pumping heavy blood against a relentless downward pull, must work twice as hard just to keep you conscious. The simple act of standing up sends your heart rate skyrocketing, burning energy at a frantic pace, akin to running a marathon while standing still. Blood pools in your legs, refusing to circulate, leading to potential blackouts or grayouts simply from rising too quickly. Movement becomes a tactical negotiation with physics. Every step is a squat lift. A simple stumble, which would be a minor embarrassment on Earth, becomes a life-threatening event here. Falling under 2.2 g means hitting the ground with twice the kinetic energy. Bones snap, joints dislocate, and tissues rupture under forces they were never designed to withstand. This is the first layer of the prison, the physical inability to explore. You are not a pioneer here. You are a prisoner of your own mass, pinned to the crust by invisible, unbreakable chains. But the gravity that crushes your bones is doing something far more catastrophic to the planet itself. We once believed that larger planets would be more geologically active, that more mass meant more internal heat driving vigorous volcanic activity and shifting continents. The original analysis of Kepler-452b suggested a flat, uniform landscape, perhaps stripped of towering mountain ranges. New geophysical models reveal that this flatness is likely the symptom of a profound geological paralysis known as the stagnant lid regime. On Earth, our habitability relies on plate tectonics, the conveyor belt that recycles carbon. Continents drift, collide, and slide beneath one another, burying excess carbon dioxide in the mantle and releasing it later through volcanoes. This cycle acts as Earth's long-term thermostat. But on a super-Earth like Kepler-452b, gravity may have broken this thermostat. Deep inside the planet, the pressure at the core mantle boundary is estimated to reach 1,000 gigapascals, pressures so immense that they fundamentally alter the behavior of rock. Under this crushing weight, the mantle's viscosity increases dramatically. The rock becomes stiff and sluggish, refusing to flow. Without the vigorous convection currents needed to drive plate tectonics, the planet's crust locks up. Instead of a dynamic puzzle of moving plates, Kepler-452b is likely encased in a single immobile shell, a stagnant lid that covers the entire world. This creates a terrifying geological paradox. The planet is generating massive amounts of internal heat from the decay of radioactive elements like uranium and thorium, heat that needs to escape. But with the crust locked tight, there are no volcanic vents or spreading ridges to release it gradually. Kepler-452b effectively becomes a planetary pressure cooker with the safety valve welded shut. The consequences for the landscape are stark. Without colliding plates to fold the crust upwards, there are likely no Himalayas, no Andes, no sharp, soaring peaks. The gravity pulls any ambitious mountain down, flattening the topography into a low, brooding expanse. But beneath this quiet surface, the heat is building. When a stagnant lid world finally releases its energy, it doesn't do so through gentle, continuous eruptions. It tends to undergo catastrophic resurfacing events, moments where the entire crust melts or fractures at once, flooding the world in magma before freezing over again for another billion years. The silence of Kepler-452b's geology is not peace. It is the silence of a bomb waiting to detonate. And while the ground beneath your feet is locked in a high-pressure paralysis, the sky above is preparing a different kind of execution. If the geology of Kepler-452b is a prison floor that refuses to move its atmosphere, is the ceiling that is slowly crushing everything beneath it. On Earth, we think of the sky as an open, limitless expanse, a gateway to the stars. On a super-Earth with 2.2 g gravity, the sky is a heavy physical lid. Gravity does more than just pull on your bones. It pulls on the air itself. A planet with this much mass grips its gaseous envelope with a terrifying strength, refusing to let go of even the lightest molecules. While Earth bleeds a small amount of its atmosphere into space over eons, Kepler-452b hoards it. Over billions of years, extensive volcanic outgassing, even from a stagnant lid, would accumulate without a mechanism to strip it away efficiently. The result is not the thin, breathable blue line we cherish, but a towering, dense column of gas that stacks weight upon weight. Models suggest that the atmospheric pressure on the surface of Kepler-452b could be tens, perhaps hundreds of times greater than Earth's. Standing on the surface would not feel like standing in open air. It would feel like standing at the bottom of a deep ocean trench. The air would be so thick it would offer physical resistance to your movements, a fluid medium that drags against you. This density creates a profound optical claustrophobia. The scattering of light through such a thick medium would likely wash out the sun into a diffuse, blinding glare. There are no crisp shadows here, no visible stars at night, and no clear view of the cosmos. You are wrapped in a perpetual opaque shroud that isolates you completely from the universe outside. But the true danger of this thick blanket is not just its weight, it is its efficiency as a thermal trap. A dense atmosphere acts as a super insulator. It allows high-energy radiation from the star to punch through and strike the ground, but it ruthlessly blocks the lower-energy heat trying to escape back into space. This is the pressure cooker effect. On Earth, a sudden rise in CO2 is a climate crisis. On Kepler-452b, with its massive atmospheric volume, the potential for heat retention is exponential. The planet effectively wraps itself in layer after layer of thermal insulation, turning the surface into a kiln where temperature regulation becomes a losing battle against physics. The walls of this atmospheric prison are closing in, but it is the warden, the parent star Kepler-452, that is turning up the heat. This is where the 1.5 billion year age difference transforms from a statistical curiosity into a planetary death sentence. Stars like our Sun and Kepler-452 are not static light bulbs, they are evolving nuclear engines. As they burn through their hydrogen fuel, their cores contract and heat up, causing the outer layers to swell and brighten. At 6 billion years old, the star Kepler-452 is emitting approximately 10% more energy than our Sun. For a planet sitting at the same distance as Earth, this extra energy is catastrophic. It pushes the planet past a thermodynamic tipping point known as the moist greenhouse limit. On Earth, our atmosphere has a cold trap in the upper troposphere that freezes water vapor, keeping it close to the surface and preventing it from reaching the edge of space. On Kepler-452b, the intense stellar flux smashes this trap. The heat becomes so intense that the oceans begin to evaporate aggressively. But unlike a normal rain cycle where steam cools and falls, the atmosphere gets so hot that the water remains as vapor, saturating the stratosphere. This is the fever of a dying world. Water vapor is a potent greenhouse gas far more effective than carbon dioxide. As the oceans turn into sky, they trap more heat, which causes more evaporation, creating a lethal feedback loop. The planet becomes a sweltering sauna on a global scale, but the tragedy deepens at the atomic level. When this water vapor rises high enough, it is exposed to harsh ultraviolet radiation from the star. Without a magnetic field to deflect the solar wind, a likely scenario if the planet's core has solidified due to high pressure, the UV light rips the water molecules apart in a process called photodissociation. The hydrogen atoms, being the lightest element in the universe, might finally find the energy to escape the planet's gravitational grip, bleeding out into the void. The oxygen is left behind, reacting with surface rocks to create a rusty, desiccated wasteland. We are likely witnessing a planet in the midst of a slow-motion execution. The oceans that might have once harbored life are bleeding into space atom by atom. The surface is transitioning from a biological haven into a sterilized hellscape, baking under a thick, wet shroud that offers no relief. If life still exists here, it cannot survive on the surface. To escape the crushing weight and the boiling sky, it would have to retreat to the only refuge left, the deep, dark wells of the planetary crust, or the last remaining pockets of high-pressure ocean. If life has managed to endure the crushing weight and the stifling heat of Kepler-452b, it would not look like us. The human form, a towering bipedal stack of water and calcium, is an arrogant defiance of gravity that only works on a mild world like Earth. On a super-Earth, our vertical architecture would be a fatal engineering flaw. To survive here, evolution would have to rewrite the blueprint of biology using the strict rules of the square-cube law. This mathematical principle dictates that as an object grows larger, its volume and mass increases much faster than its structural strength. On a world with 2.2 g, this law becomes a ruthless filter. Nature would select against height and favor stability. The towering forests of Earth would be physical impossibilities here. A redwood tree would snap under its own weight or fail to pump water to its canopy. Instead, the flora of Kepler-452b would likely be a carpet of biobunkers, thick barrel-shaped trunks hugging the ground covered in dark, rugged leaves, designed to withstand high atmospheric pressure and scavenge the dim, scattered light of the dying star. For mobile creatures, the adaptation would be even more extreme. The grace of a gazelle or the height of a giraffe represents a biological luxury that 2.2 g does not afford. We should expect organisms that resemble biological tanks. Evolution would favor low centers of gravity and redundant points of contact with the ground. Bipedalism is unstable. A trip is deadly. Therefore, dominant land animals might evolve as six-legged or eight-legged creatures, distributing their immense weight across a wider surface area to prevent sinking into the soil or shattering their limbs. Internally, these creatures would be marvels of hydraulic engineering. To circulate blood against twice the gravitational drag, a single heart would likely be insufficient. We might find organisms with distributed circulatory systems series of accessory hearts pumping in sequence, like the booster stations on an oil pipeline, ensuring oxygen reaches the brain. Their bones would be dense composite structures, perhaps reinforced with biological lattices of carbon or silica far stronger than the calcium phosphate matrix of Earth vertebrates. Flight, the ultimate rebellion against gravity, presents a fascinating paradox. While the gravity pulls down relentlessly, the ultra-dense atmosphere provides immense buoyant support. Creatures here might not fly in the way birds do on Earth. They might swim through the air. Evolution could produce sky whales organisms with vast hydrogen-filled bladders to achieve neutral buoyancy, rowing through the soup-like atmosphere with muscular fins rather than fragile wings. But even if they fill the sky and cover the ground, these beings face a final insurmountable wall. The greatest tragedy of Kepler-452b is not the hostility of its environment, but the limit of its horizon. If intelligent life were to arise here, a civilization of sturdy six-legged engineers with minds as sharp as ours, they would eventually look up at the white haze of their sky and dream of what lies beyond. But physics has built a cage around them that no amount of dreaming can easily break. Spaceflight is governed by the Tsiolkovsky rocket equation, a mathematical rule that dictates how much fuel is needed to achieve a certain velocity. It is an exponential curse. To go faster, you need more fuel, but that fuel has mass, so you need even more fuel to lift the fuel. On Earth, we sit on the razor's edge of this equation. A standard rocket is nearly 90% fuel by mass, just barely efficient enough to push a tiny payload into orbit. On Kepler-452b, the escape velocity is roughly 50 to 60% higher than on Earth. That might not sound like an impossible increase, but because of the exponential nature of the rocket equation, the fuel requirements skyrocket. To launch a payload equivalent to the Apollo moon lander from the surface of Kepler-452b using chemical propulsion, the rocket would not be the size of the Saturn V. It would need to be the size of an ocean liner or perhaps a pyramid. This creates a gravity trap. For a civilization on Kepler-452b, the energy cost to reach orbit is so astronomically high that space programs might be economically impossible before they are technically viable. They might never develop a network of GPS satellites, never build a space station, and never land on their own moon. They would be a culture of immense sophistication, perhaps mastering geothermal energy or advanced materials, yet remaining planet-bound forever. This realization offers a chilling solution to the Fermi paradox, the question of why we have not heard from aliens. Perhaps the universe is full of life thriving on billions of super-Earths, but they are all prisoners locked in deep gravity wells. Their radio signals trapped beneath ionospheres. They cannot penetrate their explorers, grounded by the sheer weight of their own worlds. Kepler-452b is a silent archive of potential a civilization that may have risen, flourished, and perhaps even died without ever being able to touch the stars. As we pull back from the crushing surface of Kepler-452b, leaving its stifling atmosphere and its silent gravity-bound potential behind, we are left with a revelation that chills us more than the cold of space. For years, we searched for Earth 2.0 with hope, looking for a second home, a backup plan, or a twin sister in the stars. But Kepler-452b is not our twin. It is our ghost. By observing a world orbiting a star 1.5 billion years older than our Sun, we have inadvertently looked into a mirror of deep time. The fate that has likely befallen this super-Earth, the relentless brightening of its star, the evaporation of its oceans, and the suffocation of its surface under a runaway greenhouse effect, is not a unique tragedy. It is the standard life cycle of habitable worlds. In approximately 1 billion years, our own Sun will reach the same luminosity that Kepler-452 displays today. When that happens, the delicate balance that keeps Earth blue will shatter. Our oceans will begin to boil, our stratosphere will saturate with vapor, and the hydrogen that makes up our water will be stripped away by the solar wind. The geological and atmospheric prison we see 1,400 light-years away in Cygnus is a preview of the inevitable death of our own biosphere. Kepler-452b is a monument to the impermanence of habitability, standing in the dark as a warning that no paradise lasts forever. This journey ends not with a roadmap to a new colony, but with a profound, terrifying appreciation for where we stand right now. We live on a razor's edge of cosmic luck. We are on a planet small enough to allow us to fly, yet large enough to hold an atmosphere. We orbit a star stable enough to feed us, yet young enough not to burn us alive. We possess a magnetic shield that the stagnant lids of super-Earths may lack. The search for exoplanets often carries an underlying escapist fantasy, the idea that if we ruin this world, there is another one waiting for us, lush and ready to receive us. Kepler-452b shatters that fantasy with the brutal laws of physics. It reminds us that Earth-like does not mean habitable, and habitable does not mean accessible. The universe is filled with worlds that are either prisons of gravity, ovens of heat, or frozen wastelands. Earth is a singular anomaly in a hostile void. It is the only place we know of where the laws of nature have conspired to allow us to stand up, breathe freely, and look at the stars without being crushed by them. The silence from the gravity well of Kepler-452b is a deafening message to humanity. We do not have a plan B. The greatest wonder in the universe is not the distant world we hope to find, but the fragile blue sanctuary we are already standing on.